Any more doubts or questions?
No, sir.
No. Okay, so we'll be starting now. So what we'll be covering today are balances and their applications. So I hope that you have already gone through those week 5 lectures, right?
Yes, sir.
The week 5 lectures. Okay. So then we'll be starting, for example, I'll give you a problem. You think about it, okay, for one or two, or maybe 2-3 minutes, and then we'll discuss it, right?
Okay, sir.
Would that be all right with you?
Yes, sir. Okay.
Okay, good. Okay, so consider this to be a circular pipe, okay? And this radius is given as r, and so this is a pressure-driven flow from the left end to the right end. Okay. Now assume laminar flow. So you basically need to find, let's call this Z. This is coordinate R, and this would be theta. Find U R U Z with theta. So this is the problem at hand. Would you like to try this for a moment? Yes? Or should we go to the solution maybe?
Solutions.
Okay. Don't
Right.
worry. Yeah.
Okay,
Yes.
sir.
Yes.
Oh,
You're something.
no, sir. No, nothing.
Oh, so you don't want to try at the moment, right? No problem. So who is Hari? Hari, can you hear me? Hari? Okay, maybe he cannot hear us. Hmm. Okay. So, there are basically 3 coordinates here, r, theta, and z, all right?
Yes, sir.
Uh, And another one could be time, right? So the first assumption is that I assume that it's a steady state problem, okay? This implies that out of just a moment. Okay, so we have a steady state problem. So this means that the time term drops to 0, right?
Yes.
Or it could be just neglected. Now we've got R, theta, and Z. Now just look at this problem really carefully. And the second assumption that we make is that you have something called as incompressible flow. Okay. And you know, if you take and the third is also a fully developed flow. Do you understand what do you mean by FD flow, fully developed? You do?
No.
Okay, so we'll discuss
I
it.
think
Okay.
I think velocities will not change after
Mhm.
fully
Yes.
developed.
Yes, you are close, but not precise. No problem. We'll cover it up. So just assume that for a moment, this is your cross section, the circular cross section. Okay. Now, at this point, you'd be having some velocity uz, and you might also be having some velocity ur, and you might be having some velocity u theta. So so r vector cross theta vector would be equal to z vector, right? For a right-handed coordinate system. This is valid. Anyway, so you know, this problem is symmetric, right? So if I say that at a certain point called r, let's call that r prime, theta prime, z prime, there is the value of ur is something like, let's say, k, okay? K could be any number, a real number, okay? If I say this, then this would imply that I am assigning a certain direction to k, right? So this is k. Now you see this problem is entirely symmetric, right? So there is no difference between this r vector and this r vector and this r vector, right? It is a circle. So this point actually sees everything identical to its surroundings. Are you getting my point?
Yes, sir.
So this would mean that if we assume that there is a certain direction to UR, for example, this one, then this direction might say that why is the direction not in my direction? And this point would say that I'm also identical to this person. So why am I not getting the K component, right? So
Yes.
that means that if you assign a particular direction to UR, that would imply that you are discriminating against all these directions, against all R cap, right? But due to the problem being symmetric, you cannot do that. So the only way that you can have the velocity, have the UR in all directions is when UR is identically zero, right? Do you get this analogy maybe?
Yes.
So UR must be identically zero at this point, so that this direction would now say, oh, it's zero, so it's no problem. It could be pointing anywhere because it's zero anyway. And this direction would be saying the same thing, that since it's zero, it doesn't matter where it's pointing. It's even if it points somewhere, it's actually not pointing anywhere because it's just zero, right?
Yes.
So a similar analogy may be followed for u theta, because u theta direction is also identical, because u theta would be something like this one. For example, this is theta, right?
Yes.
The u theta would be saying that if this direction is having a non-zero component of the velocity, why not me? I'm also identical to this one, right? So
Yes.
the only way that u theta can be identical to all the directions would be when u theta is equal to zero. So now you know that UR is equal to U theta is equal to zero, right? Now the question is about UZ. What about UZ? UZ is the actual velocity. It cannot be zero, of course. Now that is what we need to calculate. So for an incompressible flow, do you know that the divergence of velocity is equal to zero? Yes?
Actually, I forget.
Okay. So should I maybe start with deriving this entire thing, or we can take it as a condition and move on?
Oh, we will take in conditions. Okay, sir.
Okay. So let's assume that you know that for incompressible flow, this part is equal to zero. And how does this actually come? This comes by for incompressible. What does incompressible mean? That the volume of a certain body will never change, right? That is what it
Yes.
means to be incompressible. So you set the condition d of v equal to zero for a certain, let's say, fluid volume like this, an arbitrary fluid volume.
Yes. Actually, I got it's okay, sir. Mass
Yes.
continuity from it is mass continuity equation.
Yes, basically. So what I was trying to tell you was about the mass continuity equation. So people actually confuse between the incompressible flow and the mass continuity equation. So it is not really a mass continuity. It is of an identical form, but the principle behind incompressibility is this. So the change in volume due to any external pressure would be zero. All right.
Okay, sir.
Now, what does the mass continuity imply is something different, something more general. So incompressible flow is a special case of mass continuity
Yes.
with where rho is equal to zero, rho is equal to constant.
Yes.
Okay. Anyway, so you know that. And what does the grad sign mean? This is del x. Let's say this is something like this. Del r vector plus del theta vector plus del z vector. Okay.
Okay, sir.
So these are del by del r. This is del by del theta. This is del by del z. It is r minus 1. Or you might have been familiar with this form, del x cap plus del y cap plus del z cap, right?
Yes, sir.
Okay, so now you write del dot u vector is equal to del over del r of u r plus 1 over r del by del theta of u theta plus del over del z of u z. And since this is 0, this is 0, so you get del uz over del z equal to 0, right?
Yes, sir.
What does this mean? This means that this uz is
Constant.
not a
Yeah.
function
Okay.
of z, right? So if this might be the case, du by dz equal, then you could have maybe said that uz is a constant. But in
Okay,
this
sir.
case, this is a partial derivative. So you cannot say that, for example, let me give you a quick example, right? X squared plus y squared plus z's, yes, x squared plus y squared. For example, you have a function called x comma y comma z equal to this. Now you can write del f by del x is not equal to 0, and x comma y not equal to 0. I'm specifying this, right? And del f by del y is not equal to 0 for sure. Now del f by del z is equal to 0, right?
Yes.
Because there's no z here.
Yes.
But f is not constant, right?
Yes. Yes. Yes.
So that's how this inference is being made. So uz is not a function of z. So, and now due to symmetry, right? Due to symmetry, you can always write that del by del r of anything is equal to del over del theta, r times of anything equals to 0, right?
Yes.
We saw this earlier, right?
Yes, sir.
How all these directions would be quarreling amongst themselves to claim that the components in their direction should be non-zero. So effectively, we'll be having 0. This is an intuitive concept, okay? So this would effectively mean you need to actually understand one thing. That's that, for example, in this case, you have uz right here, right? uz, okay? Yes.
Yes, sir.
So for any r right here, there this might be the r vector at this r1, let's say, and at r2 this r vector will be different. Okay,
Okay, sir.
now since both of these vectors are already different, they have no problems in what the value of uz right here is, because due to symmetry you could have said that ur would be 0, right? But uz is in this direction. So
Yes.
it does not matter to them that at which r, what is the value of uz. because the vector is not in their direction, right? So what I said for this when del y del r was equivalent to 0 was only when your quantity in the direction of r, okay?
Okay, sir.
So since you are, so since uz is in the z direction, del by del r of uz may not be 0. Okay? Is that fine?
Okay, sir.
So it may not be 0, but it could also be 0. So we don't know. We'll have to calculate it, right?
Yes.
Okay. So since dvz over dz, now you know del, right, this is del is equal to 0. So vz is a function of r. It cannot be a function of theta, you know, because theta is the symmetric dimension.
Yes.
So vz is simply a function of r. Or this can be called, just a moment, where is that? This can be called uz equal to a function of r. So now, you know, how do you actually obtain the value of uz? So for this, we'll use a momentum balance. So you do understand that here we are transferring momentum from the left end to the right end, right? Is that right?
Yes.
So in that particular case, for example, we use a microscopic momentum balance. And let's say you consider a differential shell right here. All right, right?
Yes.
That sounds good. So assume that this distance is dr. And this is r. Now, there's one interesting thing, you know, you could also have used maybe a macroscopic balance, right? Where you could have taken the entire pipe right like this, and then perform the momentum transfer over the entire control volume like this, right?
Yes, sir.
However, the problem here is that you do not know if uz is a constant, right?
Yes.
So since uz is varying, might be varying at every point, at every direction z, so that means that you need to perform microscopic balance. That is a differential element balance. Okay, this
Okay,
much
sir.
should be clear, right? Mm-hmm. Okay, so do you know that fundamental equation? Del by del T of momentum would be equal to rate in minus rate out plus sum of forces, right? You might
Yes,
have
sir.
learned about this in one of the video lectures, right?
Yes, sir.
So for a steady state problem, this will be 0, right?
Yes, sir.
Now, how do you calculate the rate inside? Let's check out this shell, this part of the shell, okay? So this actually looks something like this, but in two-dimensional format, it just looks like this. Okay,
Okay.
so what is the pressure here? This is pH, right?
Yes, sir.
And this is PL. And this is UZ, right?
Yes.
Now, you know, there are, some other forces as well. How so? I mean, one is, the pressure, right? The
Yes, sir.
other is the shear stress. This is the normal stress, the sigma, and this is the shear stress, as you might have seen in the video, right? So
Yes.
the thing is that, for example, if you are writing tau or theta, what does this mean? This means that you have the r plane, this is r vector, and the shear stress is pointing in the theta direction, right?
Yes, sir.
So what do you think? Uh, which component would this be? If I want to write this, what type of tau would this be? Can you think about this?
Uh, to towards jet.
Tau?
RZ.
Oh, right. That's excellent. You were able to accurately identify it. Okay, so great. So we won't be discussing how we got here, right? So this is tau RZ, this is tau RZ at R, and this is tau RZ at R plus dr. All right?
Yes, sir. Yes, sir.
Just a moment. Hmm. Okay. So what is the rate of momentum that is entering this entire shell? Can we write it like this? Rho uz times 2 by r dr. This is rho, this is u, this is a, right? You're getting, right?
Yes. Yes.
U times A is the volumetric flow rate, and you multiply it by the density of the fluid, and you get the mass flow rate. Okay. This is the entering rate, right? The mass that is entering right here, and multiply this by uz. So what
Yes.
is momentum? This is the mass times velocity, right?
Yes, sir.
So del by del T of momentum would be m dot into v, right?
Yes.
So this entire thing is m dot, and this is v. Okay.
Yes.
Now, what is the rate out? Just check out this cross section. This is rho. Can you speak it out for me?
Rho uz 2 pi r dr at z equal to
Yes.
uh, um, 0. I mean z equal 0. Z equal
L
to less L. Suppose.
into uz. That's z equals to L. Right?
Yes, sir.
And now let's sum up the forces. Okay. Now this tau rz is actually, not acting on this in this direction. I think I wrote it. I was considering tau zr. Tau zr is here. So this would be something like, let's call it, yeah, tau rz, r plus dr. And this would be tau rz r, right? So because, what is the r plane? The r plane is a plane that is tangential to this one, right?
Yes, sir.
So if you consider a plane that is tangential to this differential element, and you consider a tau value that is in the z direction, however, it is on this plane. So this would imply that this aligns somewhere like this, right? The plane is the tangential plane, but it aligns in the z direction.
Yes.
So this implies that for, okay, these are the sum of forces, right? So what is the force in the r plus dr direction? It is tau r z times 2 pi r plus dr times L. This is the area, and this is at r equal to r plus dr, right? Just write this simply. Minus tau rz times 2 pi r L r. Are you able to understand this expression?
Yes.
Yes?
Yes.
Okay. So this is because the tau rz is right here. And this area is 2 pi r L, right? Curved surface area. And now the shear stresses have been accommodated. The momentum in flux and efflux have been accommodated. What is left? This, right? So you see here you have like this pH, 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 everywhere pH, right?
Yes.
So if you have this, then the further force balance, can you tell me the expression? pH times. Yes?
Oh, Area.
Huh?
I can't say.
Okay. So since this entire area is 2 pi r dr, right?
Yes.
And the pressure is acting uniformly across the area. So the total force that you can write is 2 pi r dr, right?
Okay, sir.
At z equals 0 minus PL, that is the low pressure area, times 2 pi r dr at z equals to L. Okay,
Okay, sir.
that's right. That's right. Okay.
Oh, okay. Okay, sir.
So yes. Now we go back again to this condition. We observed this, right?
Yes, sir.
So we know uz is not a function of z, right?
Yes.
So this means that uz at z equals to 0 should be equal to uz at z equals to L, right?
Yes, sir.
So what do you see here? You see the thing that's happening here? Since uz is at z equals to 0, at z equals to 0 is identical to uz at z equals to 0, L and z equals to L. This entire thing becomes 0, right? These are both identical.
Yes, sir.
So this would mean that this part becomes 0. We've got this part left.
Yes.
Let's hold this on for a moment, okay? And here, at z equals to 0, this pH is pH, of course. And at z equals to L, this is PL. So this was effectively, P cross 2 pi r dr times at z equals to 0, which is actually pH. And here it's 2 pi r, right?
Okay, sir.
So this would mean this becomes pH minus PL times 2 pi r dr, right?
Yes, sir.
Now you've got this thing. This tau rz times r plus tau rz times r, and the entire thing at r plus dr cross 2 pi L, right? Minus tau rz at r, the entire thing at r, times 2 pi L. This should be fine, right?
Yes, sir.
So this, when you put r plus dr right here, this becomes tau rz times r plus dr. Okay?
Yes.
So can you hear some background music right now?
No, sir.
No, you still cannot hear. Oh my God, it is blasting so much. So I was wondering if you were getting disturbed. Okay. So
Okay.
just let me know when you hear something, okay?
Okay, sir.
Because I will have to speak really loudly because it's really annoying. Anyway, so this becomes tau rz times r plus dr minus tau rz r times r
Yes.
cross 2 pi L divided by wait, sorry. I think I'll have to use this. Yeah. Hello.
Sir, okay, sir.
Can you hear me? Yes?
Yes, yes,
Okay, that's better. Okay, so if you write this entire thing as this, and you've already got this part, pH minus PL 2 pi R dr is equal to 0, right?
yes, sir.
Cross out 2 pi right here. And now what we'll be doing right here is that tau RZ, you write it like this. R plus, let's call for a moment this delta R, right?
Yes, sir.
Okay.
Okay.
And you multiply and divide by delta R. pH minus PL R delta R is equal to 0, right? And you write the limit as delta R tends to 0. So this thing becomes d by dr of tau RZR, right?
Yes,
At R plus pH minus PL over L times R equals 0. This is fine, right?
yes, sir.
So this entire thing becomes, let's assume this to be called as delta P by L. That's the pressure gradient, basically, del P by del X. Here it's Z. So this becomes 1 over R d by dr of tau R ZR R equal to minus del P over L. Yeah, that's it. Now, if you just solve this out for a moment, are you working it out with me? Yes? Are you working it out with me?
Yes, sir.
Okay, that's great. R ZR times R equal to minus del P by R dr. Integrate both sides, you have tau R ZR to be equal to minus del P by L R square over 2 plus C1. Right? All right.
Yes, sir.
Mm-hmm. So, so have you solved this problem in one of the lectures? No?
Right now I didn't. I finished only week 5, sir.
Okay, okay. Hmm. So from this, you can write it tau Rz equal to minus del P by 2L R plus C1 over R, right?
Yes, sir.
Hmm.
Minus D. Okay, sir.
Okay, this much is fine, right?
Yes.
Now, you might have also learned that tau Rz is equal to mu times del U R over del Z plus del UZ over del R,
Yes, sir.
right? And a negative
Yes.
sign here. Okay?
Yes. Okay.
You already know that this is 0 because U R is 0.
Yes, sir.
And UZ is a function of R, right? So this partial derivative can be converted into del UZ over del dr, right? This part.
Yes, sir.
So substitute this right here. So you get minus mu times duz over dr is equal to minus del p over 2L times r plus c1 by r, right?
Yes, sir.
Solve it further. Du by dr equal to del p over 2 mu l times r plus c1 by mu r. Integrate both sides. You have uz equal to del p over 2 pi l r squared by 2 plus c1 by mu ln r plus c2.
Yes.
Okay.
Okay, sir.
Now the next step that comes right here is the boundary condition.
Yes.
Now you need to understand how this function behaves. Since there are two constants, you need to have two conditions, two extra conditions in addition to this equation to have this system entirely fully defined, right?
Yes.
So for the boundary condition, what you can say is that at the center line at r equals to 0, uz would be finite, right?
Yes.
But here, if you put the limit uz at r tends to 0, what would happen? The first term would become 0, right? C1 by mu ln r and r tends to 0 plus c2, right?
Yes.
Okay, so this term, now irrespective of the value of c2, this could be anything, this could be 0, this could be 1 or anything, it doesn't matter to us at the moment. But this part, how does a log graph go? Like this, right? This is the graph for ln x.
Yes.
Okay, so at x tends to 0, y tends to minus infinity, right? Yes?
Tends to 0. Okay, sir.
It just goes on right here. Asymptotically, okay? So if you apply this condition right here, this would imply that uz tends to minus infinity, right?
Yes.
Because c2 is finite.
Yes.
But this is not realistically possible, right?
Yes.
So this would imply that this term should be such that the velocity does not move to infinity or out of bounds. So this necessarily implies that c1 must be 0, right? Or mu should be infinity, right?
Yes.
So in the case of highly viscous fluids where mu tends to infinity, you might be sometimes able to neglect this condition. That is a case of super dense fluids. Sometimes, or super viscous fluids. I'm sorry. Sometimes, different states of matter, but those things are for some other day, not today. So since this is also physically impossible, the only condition that we've got is C1 equals to 0. So this would imply that C1 is equal to 0, right?
Yes.
So this effectively makes us remaining this part, 2 pi L R by 2. Is this mu? Yes, it's mu. It's not pi. Okay. 2 mu L R squared by 2 plus C2, right? Now, another thing that you need to notice is just notice that at this boundary, right? This one, you have uz, right?
Yes.
But this boundary is not moving. This entire U shell is equal to 0. Our CV is fixed in space, right?
Yes, sir.
So this would mean that the no-slip boundary condition is applicable here, right?
Yes.
You understand the no-slip boundary condition, right?
Yes, sir.
Okay. So we have U z equals to 0 at r equals to r. Okay.
Yes, sir.
So this would mean that U z equals to 0 equals to del pi over 4 mu L times r squared plus C2. So C2 is equal to minus of del P over 4 mu L r squared. And Uz is finally equal to del P over 4 mu L minus plus r squared minus r squared, right?
Yes, sir.
And if you take part common out of here, 4 mu r squared by L, 1 minus r over r, the entire thing squared, right?
Yes, sir.
Now, if you are given this uz equals to this one, can you find for me uz max? Can you do that?
Uh,
Well, I know you can do it.
uh, okay. Its derivative should be do 0. Then we will find the users.
So do it and tell me. Did you get it?
No, sir.
No. Okay.
Say, something.
Yes. Sorry.
Oh, okay, so
Okay. So actually, you can just look at it right away without needing to find any sort of derivative. So uz is equal to 1 minus something positive, right?
Yes.
So if you increase this r, this entire term will keep increasing, right?
Yes.
And r can go from 0 to r, right? Big R.
Yes.
So this implies that you are subtracting something positive from 1. So this will always be less than 1, right?
Yes.
So what is the maximum value that this entire thing can take? That would mean a minimum value for this part, right?
Yes.
And the minimum value of r is 0
Yes.
from here. So this implies that uz max would be equal to del p over 4 pi l r squared.
Yes.
So uz equals to uz max times 1 minus r by r. Okay,
Yes.
good enough, right?
Yes.
Okay. Now can you find the average velocity? Yes, can you do that? So how do you define the average velocity? Let me tell you the formulation. Now you know that, for example, this is L, and this is the value y at something like x, right? Then how do you define the average? Y average would be equal to y dx integration from 0 to L divided by 0 to L dx, right?
Yes.
So similarly, for an area like this, you have u, let's say that's y at a certain area, right? So how do you define it for an area? That is the double integral from here and here. Okay? So how do you define the average velocity? You do like this, dA, double integral A divided by double integral dA times A, right? Now what is the total area? Just look at the pipe, okay? This is the pipe. And the entire area of this cross section is pi r square, right?
Yes.
So this becomes uz dA integral pi r square, right?
Yes.
Now, if you want to take a differential areal element, for example, like this one, right? We already took it once. So what was the area of this element? It was 2 pi r dr, right?
Yes.
So you can write it like this, that if A equals to pi r squared, then dA would be equal to 2 pi r dr. Now plug this value right here. This would become uz max times 1 minus r over r squared into 2 pi r dr integration from 0 to r, right? Divided by pi r squared. Now note, now you could also take a quick look right here, right? There are two surface integrals here, 2, and this is converted into 1 because we use this type of transformation. Are you clear with this?
Yes, sir.
Sure?
Yes, sir.
Okay. So this becomes uz max times r squared by 2 minus r cubed by 3. Yeah, r squared. and you have 2 outside and divided by r square. That's right. Or wrong? No, that is r square. You have r. Oh, that's r cube actually. So this is r out of 4 by 4, right? All right. So this becomes z max divided by r square times r square minus r square by 4. R square by 4, right?
Yes.
Good. That's right.
Yes.
Which becomes from here. Okay. And this is the famous, Euler problem. Okay. So any questions in this one? We've completely solved this problem. Now, can we jump to another problem then?
Okay.
Sure. Or you would like to go through this once at your own convenience and then ask some questions if you have any. Yes, should we switch? Should we take up another problem?
Yes, sir.
Okay.
Yes.
Okay. Let us suppose you have an inclined plane, okay? This is the second problem. And you have gravity right here. And you have a film. You know a film, right? A film of fluid that is flowing under gravity right here. Okay?
Okay.
Film. Now you zoom it in. And this would look something like this. Okay?
Okay.
So this interface would actually be something like this, right?
Yes.
But for the ease of modeling purposes, we are assuming it to be a flat interface. Okay?
Okay.
And let's pick our coordinates here. And here is x. So you'll be seeing that using these coordinates is much easier than when you're using the coordinates right here. So if you do it like this, x here, let's suppose x here and z here, then the problem becomes really complicated. But you can do it this way as well. There's no problem. But this one is easier, so we'll be using this for demonstrative purposes. So you can go back and check out the problem by solving from this coordinate as well. So it won't matter much actually. Okay? Yes?
Yes, sir.
Wait, this is not erasing. Okay. And you've already got G here. and you assume that this angle is beta, okay? And if this angle is alpha, then you can always write alpha equals to 90 degrees minus beta, right? You understand this part, right? Yes, can you? No response?
Yes, sir. Yes, sir.
Okay. Okay, so again, we are not doing a macroscopic balance here, and we're doing a microscopic balance. So we take a differential element layer right here. Okay.
Okay, sir.
Now, the same assumptions, you know, the first would be steady flow. The second would be incompressible flow. The third would be are you following, right?
Yes, sir. Yes.
The third would be laminar flow. Okay, so now let's start first. And from the incompressible flow condition, you've got del dot V is equal to 0, right?
Yes, sir.
We already discussed this. Now, since this is a two-dimensional problem, so we can just write del Vz over del Z plus del Vx over del X is equal to 0, right? Right?
Yes, sir.
And since this is actually a very thin film, right? Thin film.
Yes.
So this flow can be considered to be a planar flow. And due to the symmetricity of this problem actually looks like something like this. This is the film.
Okay.
This is flowing downwards. So due to the symmetricity of this problem, you can also write that Vx would be equal to 0. Okay?
Yes.
This is because we are assuming a thin film and a planar flow. Planar flow, okay? So it flows only in the Z, and this one is Y. Yes, this is Y. So it flows in the YZ plane. But since we are considering a two-dimensional case, so Y components are already neglected, okay? So finally, you've got this part goes to 0, and dvz over dz equals to 0. Now notice that this del becomes d.
Yes.
This implies that vz is a function of f of x, right? Let's call that vz of x. Okay, so now we know this. Now we start doing a momentum balance right here. Okay, so let's assume that this is your control volume. Okay.
Okay.
I'll find this momentum first. So now you see that taking your coordinate right here is a good choice because you can write this part as z equals to 0, right?
Okay.
And you write this part as z equals to L. So here you have Vz, and here you have Vz. Now, del by del T of the change in momentum, since this is a steady state problem, this becomes 0. The left side becomes 0. Rate inside would be equal to rho Vz, right?
Yes.
Times this thickness is dx, right?
Yes.
So rho Vz into dx. And internally, let's assume that the dimension is b. So this is b, okay? And also b is much, much greater than the x dimension, right?
Yes.
So what is the area? Dx times b. Area times velocity, that's the volumetric flow rate, and multiply this as the mass flow rate. And the mass flow rate times the velocity again would be giving you the momentum, right?
Yes.
At z equals to 0. That's the inflow, and the outflow can be written as this way. B dx Vz times z equals to L, right?
Yes.
Now write the pressure condition. This is P times B dx at z equals to 0 minus P times B dx at z equals to L. Okay? Now we equate these stresses, right?
Yes.
Plus,
Gravitational.
yes, that will also come. So, okay. Now, xz times what is the entire area, This is L times B, right?
Okay.
This is the force at, and this coordinate, since, x equal to 0 was here, and this is x equal to x, and this is x plus dx. So this coordinate is x, and here you have the fluid, right? And minus tau xz L cross B x plus dx, right?
Yes.
Plus, if this is g, then this is g cos beta, and this is g sin beta. Okay. So the other force that you have is rho g cos beta. This is the component of the acceleration, and multiply this by BL. Okay.
Okay.
Because BL is the area, and multiply it by the by dx. This is the volume of the entire element, right? This is b. So this, the inside dimension, this dimension is b, and this is dx, and this is L. What is the volume of this cuboid? It is BL into dx. This is the volume, right?
Yes.
This is the density. Density times volume will give you mass. And mass times acceleration, it will give you the force, right?
Yes.
So is this entire formulation clear to you?
Yes, sir.
Okay, so if it's clear, then that's an excellent response. Okay, so now the thing is that since we had dropped this film from the top of the inclined plane, right?
Yes.
We just dropped it from here, so it is flowing freely, right? Free flow.
Yes.
So can we say that Vz at x at z equals to 0 is equal to 0?
Yes.
Because this case is identical to when you drop a ball from a tall building. So in this case, you take u equals to 0, right?
Yes.
So this part becomes 0. And this is something we do not know, right? Vz at z equals to L. We don't know this, right?
Yes.
Okay. Yes. So from this condition, we know that Vz is equal to only fx. Vz is not equal to f of x comma z, right?
Yes.
So this implies that Vz at z equals to 0 would be equal to Vz at z equals to z would be equal to Vz at z equals to L, right?
Yes.
So what is Vz at z equals to 0? That is 0, right?
Yes.
So that implies that Vz at z equals to L is also 0. So this is also 0. Okay?
Okay.
Now, obtain Pz equals to 0. Since this entire film at both these ends, look at this geometry right here. This is exposed to the atmosphere, and this part is also exposed to the atmosphere, right?
Yes, sir.
So this implies that P at z equals to 0 is equal to P at z equals to L,
Yes.
which is equal to P atmosphere. Okay,
Yes. Yes.
good. So since this is now P atmosphere, this is also P atmosphere. So both of these terms are identical, right?
Yes.
So they cancel out. Again, now you take BL common, and tau xz at x minus tau xz at x plus dx plus BL common rho g cos beta dx equals to 0. Okay.
Yes, sir.
Now, for a moment, just cancel out these terms first. For a moment, assume that we can write this as tau x minus tau xz x plus del x divided by del x and multiply by del x plus rho g cos beta del x. Okay. You have limit del x tends to 0. Can you write this entire expression like this?
Yes.
Good. This is good enough, right? And once you have this thing just looks like d tau x z by dx, right?
Yes.
The first principle of derivatives. F of x plus delta x minus f of x divided by delta x equals to f prime x.
Yes.
Limit delta x tends to 0. And this situation is identical to this one. So we write delta x plus rho g cos beta delta x, and both of these also get cancelled since delta x is not equal to 0. It is tending to 0, but not equal to 0, right?
Yes.
So finally, what happens that you have an equation that reads as x equal to rho g cos beta, right?
Yes.
Now you can write tau xz equal to minus mu times. What do you write it as? We just discussed it earlier. Can you tell me, please?
Dux by
Dux by
dz. Yes.
That's it.
Yes.
So there will be this term as well.
Z by dou x. Okay.
Yes, right. So you missed this out. So notice that this is not simply, tau x that you can just write del u by del x. This is tau xz.
Okay.
And interestingly, if you write tau zx equals to minus mu times du z by dx plus du x by dz.
Yes.
Both of them are identical actually, right?
Yes. Yes.
So this would mean that since this is 0 already, we know this, right?
Yes.
This becomes minus mu times du z over dx. And so the entire thing becomes du z over dx equal to minus rho g by mu cos beta. So uz equals to minus rho g by mu cos beta times x plus c1, right? This is clear, right? Yes?
Yes, sir.
Okay, since this part is clear, now we need to find out c1, right?
Yes.
Now assume film thickness as TF film, okay? So this film is extending from x equals to 0 to x equals to TF, okay?
So I think
Yes, any questions, any doubts?
so before evaluating tau, what was that, sir?
Which one? Sorry?
Yes. Before evaluating, we I mean d tau xz by dx equal to rho g cos beta ka, sir.
Right.
Again, we are derivating. First of all, we have to derivative tau x.
Okay. Oh, right. I'm sorry about that. Yes, you're right. Perfect. Good point. So this means that you are actually paying attention. That's good. I just missed this out. Sorry. Okay. So where were we? So this becomes d by dx of minus mu duz over dx is equal to rho g cos beta, right?
Yes, sir.
Assume mu constant. Okay.
Yes.
So this becomes d by dx of duz by dx is would be equal to minus rho g cos beta over mu. All right.
Yes.
Now this becomes du z by dx is equal to minus rho g by mu cos beta x plus c1, and uz is equal to minus rho g by mu cos beta x squared by 2 plus c1x plus c2, right?
Yes.
Now you need to see that outside x equal to 0 you have air, right? Air. Yes?
What's that?
Outside x equal to 0, at x equal to 0, you have air, right? This surface is exposed to air.
Yes, sir. Yes.
Exposed to air. Okay. Now just check out this really small control volume right here. Okay.
Okay.
This is the fluid, and so due to the presence of the air, you have a certain tau xz acting on the fluid, right?
Yes.
Air to fluid. And you will be having an equal and opposite reaction on the air, right?
Yes, sir.
This would be tau xz. Fluid to air. Okay?
Okay. Sir.
Now, you know that tau xz, F2A, fluid to air, would be given as mu air times del u x by del z plus del u z by del x, right?
Yes, sir.
And this is 0. And tau xz at from air to fluid will be given as minus mu of fluid times del uz over del x, right? I won't be writing these things, okay?
Yes.
In the air, in the fluid, right? And since by the third law of motion, you have F to A would be equal to tau xz, A to F, right?
Yes.
This implies that mu air duz over dx air would be equal to mu F duz over dx in the fluid, right?
Yes, sir.
So duz over dx in the fluid is equal to mu air over mu F times duz over dx in the air, right? For equilibrium. This should be clear, right?
Yes, sir.
Now, you know that mu A is much less than mu F, right?
Yes.
Since this is a gas and this is a liquid.
Yes.
And you also know that duz over dx is F is finite, right?
Yes.
So this would mean this part is much less than 1, right? So this entire thing would be something like 0.00000 approximately, like this one, something, right? Yes?
Yes. Yes.
So this implies that duz over dx in the fluid at x equals to 0 would tend to 0, right?
Yes, sir.
So you get another boundary condition right here. See this?
Yes.
So using this condition right here, if you put x equals to 0 right here, then the C1 would be C1 equals to 0.
Yes.
Now I hope you understand the reasoning behind us taking x equal to 0 at this surface and not this one.
Yes.
This is how we are using this condition. So since C1 is 0 now, then you can simply write that uz equal to minus rho g by mu x cos beta plus C2. Okay?
Yes.
And at x equals to delta, x equals to, sorry, TF, you have the no-slip boundary condition, right?
Yes.
Why? Because it is touching the inclined plane, this one.
Yes. Yes.
So now assume that there is another possibility that is here, that assume that the inclined is moving at a velocity of u inclined right here. Okay?
Okay.
Then can you apply the no-slip boundary condition here?
No.
No. So what will you do? You will, this is beta, right? So this would be 90 minus beta, and this is beta again. And this is basically 90 minus beta. So this velocity would be u inclined sine beta, right?
Yes.
So at this point, you can write uz at x equals to tf is equal to 0 in the original condition, but here you'll have to write uz at x equal to tf is equal to u inclined sine beta.
Yes.
Good?
Yes. Yes. Yes.
Yes.
Sir.
So using this, you can write that, wait. Oh, this is cos beta x squared by 2, okay. This thing, right?
Yes.
So 0 equals minus rho g by 2 mu df squared cos beta plus C2. So C2 equals rho g by 2 mu df squared cos beta.
Oh.
And this implies that uz equals to rho g by 2 mu cos beta df squared minus x squared, right? Is equal to minus rho g by 2 mu good. You understood this entire problem, right?
Yes. Sir. Yes.
So these were actually, really long problems. So this took a long time to solve. And after this, just a second. Can you find uz max?
Yes.
So tell me the value. Yes, what will be the value of uz max?
Rho g cos beta by 2 mu.
CF square, right?
Yes.
Okay, good. So similarly, you can probably also calculate the uz average value, right?
Yes.
Which will be uz times dx times b integrated from 0 to df divided by integral dx times b 0 to df. Agreed? Do you agree, right?
Yes, sir. No.
Okay.
Yes, sir.
Good. So next time, we'll be continuing with this similar balance problems. So, did you like these two problems that we discussed today?
Yes, sir.
So one was based on the cylindrical coordinates, and the other was Cartesian, but it was a bit difficult in terms of you had gravitation as well, right?
Yes.
So, any comments, or what should we take up for the next class, or something you want to say? Some suggestions, something?
No, sir.
Any questions in both of these problems?
Understood, sir. Actually.
Understood. Okay, good. So these are, two really fundamental problems that actually govern a lot of physics further. So because a similar type of problem would be a flow between parallel plates, right?
Yes, sir.
So you can use the concepts used in this problem and the circular problem to solve this one. And you can even solve this in the presence of gravity, right? Because you just have to do how to do this, just like you did this.
Yes.
So that is why I took this one as standard benchmark problem. So, so great. So next time as well, you can bring some of your own doubts, and we'll first discuss that, and later we'll start with our own problems. Okay.
Okay, sir.
So anything else you'd like to share or comment? Yes? No?
Yes, sir. Excellently, teachers. Excellently taught, sir.
Oh, thank you. I thought that, well, I'm thankful that you are able to understand everything. These are actually not simple problems, so these are fairly complicated, and if you just encountered them in practice anytime somewhere other place, then it will be really difficult to think how to approach these problems. So next time, probably we'll be taking up some energy and heat transfer problems. And so you must watch all those lectures really carefully. Okay, watch
Okay, sir.
lectures. So because the next time the problems that I'll be taking will be really complex.
Okay, sir.
So in that, you need to have a clear understanding of the basic concepts. So that's how we'll be able to approach these.
Okay.
Okay. And soon I'll be uploading all these videos on the YouTube channel, so you'll probably get your get those links to them. Okay. That will happen soon.
Okay.
And also, all those, I think you missed out the last session in which you were unable to attend. So you can just go through the lectures of that week. So I'll just tell you what we did during that week.
Okay, sir.
Okay, so we discussed a bit about solving nonlinear systems of equations, like this one. If you have 1, 2, and multiple equations and multiple variables, like 4 equations and 4 variables, right?
Yes, sir.
Then how to solve them? I think you were a bit stuck in these type of problems, right?
Yes, sir.
So we will take, if you want, we could take these up in the next session. And the next problem that we did was the emptying of a water tank that has an area of something like this and an orifice area of this 1 centimeter. So we did some mass balances, and this was a fairly simple problem. I think you might have done this earlier as well, right?
Okay, sir.
Also, you might have heard of the Navier-Stokes equations, right?
Yes, sir.
So do you know how to prove them? Do you?
What's that?
Do you know how to derive these equations? Derive the Navier-Stokes equations. If I give you a problem that derive the Navier-Stokes equations, can you do that?
At the land, but I forgot, sir. I have to remember again, sir.
Okay, so just go through that proof if you can once, because that will actually help you in clearing a lot of concepts about tau xz and tau zx and all those things.
Yes, sir.
So you actually take, I can give you a hint of the proof if you want, or you can just refer to one book called Soam Biswas, you might have heard about it in fluid mechanics.
Yes.
So what you do is that you take a differential cube, a little volume of this might be delta x,
Yes, sir.
and this might be delta y, and this might be delta z, and you calculate the stresses at each of these spaces, this one, and you use those formulations, tau ij equals to mu times del ui by del xj plus del xj plus del uj by del xj by del xi, right?
Yes.
And tau I, this is for I naught equals to j, and tau I would be equal to I think the pressure terms, right? Plus some other terms. So these are big terms, that give you these types of formulations like u x plus u y squared, this type of terms. Okay. So if you can, then just take a look. So we won't be discussing the proof of the Navier-Stokes problem, Navier-Stokes equations in the next class, because they are really time consuming, so we cannot spend that much time in those. But if you want, we can extend the session or prepone the session for 1 hour, so that we can for maybe 30 minutes, so that we can discuss what we actually want to do. Okay.
Okay.
So that will be up to you. So, but I can assure you that if you are well versed in deriving the Navier-Stokes equations problems, then all of these balances will be really a cakewalk for you. Okay.
Okay, sir.
Okay. So just revise these 2 problems that we discussed today, and let's meet on Tuesday next time. Okay.
Okay, sir.
Okay. And if you are unable to somehow, come to the live session on Tuesday, then you can just drop a mail to me. Yeah, I already told you my email ID, I think. Yes, this one.
Yes, sir. Yes.
This is SHIVANGRP
Yes.
at mechanical.itd.ac.in. Okay.
Yes, sir.
Okay. Good luck
Thank you, sir.
and best wishes for your child.
Thank you. Thank you, sir.
Okay. See you on Tuesday. Okay.
Okay, sir.
Okay.